Hello students, welcome to the second session of our first module, subject refrigeration and air conditioning, RAC. So students, in the previous session we have studied about the basics of refrigeration, how is it different from air conditioning, and brief history of refrigeration and all, and the basic and the unit called tonnage of refrigeration. Okay, unit, we have defined the unit of refrigeration and the value of 1 ton. We have calculated value of 1 ton. Hope you remember 1 ton equal to 3.5 kilowatts, or around 210 or 211 kilojoule per minute. So this is how we define unit of refrigeration. Now we will move on to the parameter to measure the performance of the refrigerator. So students, you might have learned the heat engine, right? So how is a heat engine working on in a cycle? Source temperature T1, sink temperature T2. It will absorb a Q1 amount of heat from source and reject Q2 to sink, and will give a work of W. In the case of heat engine, we use a parameter called efficiency, thermal efficiency. Thermal efficiency equal to input by output. So here input is our heat input Q1 by not input by output by input. Output by input. So our output is nothing but work, input is heat, right, Q1. So since by first law of thermodynamics, Q1 minus Q2 equal to W, right? Therefore efficiency equal to W, right? So Q1 Q1 can be written as Q1 W can be written as Q1 minus Q2 by Q1, right? Gives efficiency equal to 1 minus Q2 by Q1. This is how we calculate the thermal efficiency of a heat engine. So students, you have already understood that refrigerator is exact opposite of heat engine, right? Heat engine. So how can we draw the schematic diagram? Here we have a refrigerator. Here a sink temperature or cold space to be cooled T2, the space to which the heat is rejected. Okay, so we have to add a work here. So Q1 is the amount of refrigeration is Q1, amount of refrigeration effect required is Q1, Q2 amount is rejected to T2, W is the amount of work we are providing, right? So here by first law we can write that Q1 plus W will be equal to Q2, right? So here we will define a parameter called COP. What is COP? Coefficient of performance. Instead of thermal efficiency, in case of refrigerator we use a parameter called COP. So students, you must be very much aware of this particular. You must have this parameter every time in your mind. So whenever you use the Whenever you learn about refrigerator, you have to be thorough with the concept called COP. COP is the parameter that is used to measure the performance of refrigerator. So COP is nothing but coefficient of performance. COP is defined as COP equal to desired effect by work input. Desired effect by work input. That is how we define COP. Okay. So in case of refrigerator, Q1, Q2, W work added. Here COP will be equal to, what is the desired effect? Desired effect is amount of heat that is being extracted from the space, cold space, or the space to be cooled. So that is the desired effect, Q1 by W. But you know, Q1 plus W equal to Q2, right? So W can be written as Q2 minus Q1, right? Therefore, COP equal to Q1 by Q2 minus Q1, right? So this is how we write COP for refrigerator. On the other hand, we also have a device called heat pump. Heat pump is exactly same as refrigerator itself, working is same as refrigerator itself, but the desired effect is different. Yeah, you have to remember T2 will be always greater than T1. Okay, you must remember that point. Here also work is added, work in case of heat pump, WHP. Therefore, our desired effect is this one. Q2 is the desired effect. We are not bothered about cooling a space. We are bothered about heating a space. So this is the heating space. Sure. This is the heating space. This is the cooling space. Okay. So basically heat pump and refrigerator similar in working, but the desired effect is different in both cases. In refrigerator, we are more concentrated on extracting heat from a colder space and rejecting to another space which is at a higher temperature. But in a heat pump, we are concentrated on supplying heat to a warmer space by extracting heat from a colder space. So the effect is different in both cases. So here COP of heat pump is nothing but Q2 divided by W, right? So Q2 will, W is nothing but Q2 minus Q1 itself, right? Right? So students, COP of refrigerator equal to Q1 by Q1 minus Q2. COP of heat pump is nothing but Q2 by Q1 minus Q2. So students, if you add COP plus 1 means Q1 by Q1 minus Q2 plus 1 is Q1 plus Q1 minus Q2 by Q1 minus Q2. Sorry. Q2 minus Q1 plus 1. Q1 by Q2 minus Q1 plus 1 equal to Q1 by Q2 minus plus Q2 minus Q1 by Q2 minus Q1, right? So this Q1 cancel, you get COP refrigerator plus 1 equal to Q2 by Q2 minus 1, right? So this is nothing but COP of heat pump. So the relation between COP of heat pump is COP of refrigerator plus 1 if both are working between same source and sink temperature. This is very important. This is only applicable when the temperature range between the range of temperature in which both the refrigerator and heat pump are working are same. Okay, then only this is applicable. If they are if both are working in different temperature range, then this relation won't be applicable, right? So T1 and T2 source and sink temperature is same in must be same in both cases, then only this equation is valid, right? Okay, so students, I have drawn a figure like this: T1, T2 work, Q1, Q2. So this is a simple diagram showing the working of refrigerator. Actually, students, this is the refrigerator. Actually, in this refrigerator, there must be a working fluid. This is working on a cycle. This refrigerator is working in a cycle. Actually, a particular fluid, a working fluid will be there. This fluid will undergo a cyclic process. So that is what we have to learn in detail. Okay. So what is the working of refrigerator? What are the working? What is the fluid which undergo the working fluid which undergo the cycle? What is the cyclic process? How is that this process is defined? What are the different process taking place? Okay. So all these things we have to learn, right? So the very basic of working fluid, which because in case of engines you might have studied air standard cycles. Similarly, in refrigeration also we have working fluid as air. Actually, this is only a theoretical cycle. It is no, it may not be. It is not usually used in for practical purposes and all. For the purpose of study only, we are defining air refrigeration cycle. Air refrigeration cycle. Air refrigeration cycle. So what is the peculiarity of air refrigeration cycle? Here the refrigeration is working using air as the working fluid. Okay. So what are the specialties of air? Why? Or what are specialties? Specialities. So air must air it does not undergo any phase change. Air won't undergo any phase change. Phase change means actually air is in its gaseous form. Whenever it absorbs heat or it reject heat, it won't undergo that much of what phase change. It won't get transferred. It won't be changing into its liquid state. Okay, so there is no phase change during the cycle, right? It takes or reject sensible heat only. What is sensible heat? Sensible heat is nothing but that particular heat which will enable the change in temperature only. There won't be any phase change. That particular heat which enable phase change is called latent heat. So in case of air, there won't be any latent heat, right? Latent heat. It does not absorb or reject a latent heat because it doesn't change its phase. So students, hope you understood the idea. So the power required to operate the unit will be higher in this case, right? Because the amount of sensible heat that air can absorb or reject may be very less compared to latent heat. So we have to operate this system or cycle at a higher power. Higher power means lower COP. So that is why air system is not practically used. But just for the sake of study, we will be studying air refrigeration cycle. So what is the, I will show you the diagram. It will, there are two types of air refrigeration system: open air refrigeration system. In this system, you will have a cabin to be cooled, okay? Some compressor, cooler, expander. So this is expander. So this is compressor. So this is cooler. This is refrigerator. Refrigerator is a cabin. By refrigerator we mean the cabin or the space to be cooled. Okay. So this is how a systematic diagram looks like for an open refrigeration cycle. So students, through this four different devices, the air flows. Air acts as the refrigerant or working fluid. Air is the working fluid. Okay. So how does it work? So the air will takes up heat from, the air will extract heat from the refrigerator. It get compressed, then it move to compressor where it get compressed to a higher pressure and temperature. Then it reach cooler where it reject heat to outside ambient or warmer conditions, and it thus its temperature gets reduced. Now it reaches expander where its uh, pressure get reduced, even temperature and pressure both get reduced, and again it reaches refrigerator where it can again extract heat. So that is the cycle. That's the cycle through which air passes, or the cycle that air undergoes, so that continuously heat can be extracted from cabin and continuously it can be rejected to the ambient temperature. So in this case, the air is in direct contact with the space. Okay, air is directly passed over the refrigerator space to be cooled. So cooler air from expander enters the cabin and comes in contact with the occupants or the objects. So that is why we call this open air refrigeration. We will learn the working in detail in the coming sessions. Now, as of now, you just make sure that you understand the four different devices that are required in case of an air refrigeration cycle. Okay. Now I will move on to the second type. What is that? Closed air refrigeration. Closed air refrigeration cycle, or dense air refrigeration cycle. Closed or dense air refrigeration cycle. Okay. So here the equipments are same: cooler, compressor, refrigerator, refrigerator expander. Okay, this compressor, refrigerator, cooler, expander. Okay, this is how flow of air takes place. Here, in case of closed air refrigeration cycle, a refrigerator is the circulated air doesn't have contact with the refrigerator space. Okay, here there is no direct contact between the working fluid and the product being cooled. Okay, then how cooling is taking place? Actually, cooled air is always passed through pipes of various components of the system at all time. So it is passed through some pipes or ducts. It is the air is not allowed directly to come in contact with the objects or occupants to be cooled. It is usually passed through pipes. That is why the system is called closed air refrigeration system. Okay, so it is passed through pipes. The transfer of heat takes place across the surface of pipes or ducts. Okay, so there is no direct contact between working fluid and the product being cooled. So that is the difference between closed and dense air refrigeration, closed and open air refrigeration cycle. So cooled air from expander passes through the coil or pipes, and a fan circulates and recirculates cabin air over those pipes. So there will be air in the cabin or a room. So this air will be circulated over the pipe through which the working fluid air is passing. Cold air is passing. So the outside air is allowed to pass over the refrigerated air which is passing through the pipes. I will show. So this is the refrigerator. So this is some coil through which air is passing. The outside air is made to recirculate. The black represent outside air. So this air is allowed to recirculate or circulate all around the pipe. So there will be a heat transfer. This heat transfer from the outside air to the air inside the coil. So that is what happening in closed refrigeration cycle. So what are the advantages of closed air refrigeration cycle? Since it can work at a suction pressure higher than that of atmospheric pressure, volume of air handled by compressor and expander will be smaller. So have you understood the advantage? In case of open refrigerator cycle, the air will be in directly contact with the objects or the occupants, right? It means it is open. The air is open to the space. So the pressure of the air will be around atmospheric pressure only. So very low pressure. Okay. So since that is the input for compressor, I will show expander, refrigerator, compressor, cooler. Compressor. So students, in case of closed refrigeration cycle, the pressure, this is the input pressure for compressor, this is the output pressure. So the output pressure by input pressure is the pressure ratio. So here, since this air is moving through the closed conduit itself, the pressure here will be higher itself. that is at the input of compressor will be higher itself. So the pressure ratio for a closed system will be not that much higher. But in case of open refrigeration, so this will be open to the atmosphere. Atmosphere pressure will be a lower pressure compared to the pressure inside a pipe. So the input pressure in case of closed open system will be very much lower. So the pressure ratio required for the compressor to reach this output pressure will be even higher. So the compressor should work at a higher pressure ratio, the suction, right? So what will happen? Since the operating pressure ratio or compression ratio can be reduced in case of closed system, the COP in case of closed system pressure ratio is lower. Open system pressure ratio. So compressor is doing nothing but increasing the pressure of the system, right? Pressure of the working fluid. So the pressure ratio will be higher in case of open system. So higher pressure ratio means you have to increase to a higher pressure means you have to add more work. So the work input will be more, right? Work input will be higher. Here work input will be lower. So work input lower means COP will be how work is related to COP. COP is nothing but Q by W means W higher means COP lower. COP sorry W low higher means COP lower, since they are inversely proportional. W lower means COP higher. So in case of closed, so this is so in case of closed refrigeration system, work pressure ratio is lower, therefore work is lower. So the COP will be higher. In case of open system, work will be higher also, therefore COP will be lower. So that is the difference between closed and dense refrigeration cycle. So students, in case of heat engine, the basic cycle which yield maximum thermal efficiency, or eta. What was that? Carnot cycle, right? Therefore, heat engine is opposite to refrigerator, right? Since heat engine is working based on Carnot cycle, this is the basic cycle which yield maximum efficiency. So this must work on what? A reversed Carnot cycle. Reversed Carnot, right? Reversed Carnot. So what are the process involved in Carnot cycle? Carnot cycle process. What was that? Do you remember? Those were two reversible isothermal processes, right? Isothermal compression and expansion. Two reversible adiabatic compression and expansion, right? So in case of reverse Carnot cycle also, the process remains changed but the direction only. A reversed Carnot cycle process remains same, but direction is reversed. So that is the difference between Carnot and a reverse Carnot cycle. Then I will draw in PV diagram reversed Carnot cycle. Okay, reversed Carnot cycle, RCC, right? So here we will have a reversible isothermal. I will draw once more. PV RCC. Okay, we will have a sorry. One, two, three, four. So this is a reversible adiabatic compression, right? Since volume is getting reduced, it means compression. Pressure is increasing, right? So reversible adiabatic compression, PV raised to n equal to constant. Here temperature, this is reversible isothermal compression, T equal to constant. This is PV raised to n equal to constant, reversible adiabatic expansion. So this is again T equal to constant, reversible isothermal expansion, right? Isothermal expansion means volume is increasing, pressure is decreasing. In expansion process, volume increase, pressure decrease. In compression, volume decrease, pressure increase. So that is the difference between expansion and compression. So these two. So these two adiabatic, right? These two isothermal. So these are so here the direction is anti-clockwise, right? In case of Carnot cycle, it was clockwise. Processes were the same. All the four processes were the same, but the direction was like in clockwise direction. In case of RCC, reverse Carnot cycle, it is in anti-clockwise direction. So students, I will draw it once more. Adiabatic compression, isothermal compression, adiabatic expansion, isothermal expansion. So students, two adiabatic process means there is no 1, 2, 3, 4. So 1 to 2 adiabatic process. So here adiabatic process means Q equal to 0. There won't be any heat transfer. Similarly, 3 to 4 adiabatic what? Adiabatic expansion, right? Here also Q equal to 0. So these two processes there won't be any heat transfer. But in case of isothermal process means 2 to 3. Temperature remains constant, but there will be a heat transfer. 4 to 1, temperature will be constant, but there will be a heat transfer. So since 4 to 1 expansion is taking place, the working fluid air to expand, how the heat transfer should be done, whether heat rejection or heat addition, how air expands when it absorbs heat, right? When it absorbs heat from a space. So here 4 to 1 Q refrigeration takes place. Q refrigeration means it extracts heat from the space to be cooled. So air absorbs heat from the space, that is rejection, no, Q absorption, QA. So in case of 2 to 3, the air gets compressed, right? The process is isothermal compression. So in order to get compressed, the air must reject heat. So here Q rejection takes place. Q rejection takes place. So 4 to 1 absorption of heat. Absorption of heat at T constant, constant temperature. 2 to 3 rejection of heat at constant temperature. So these are the process. In case of adiabatic, reversible adiabatics, expansion and compression, there is no heat transfer. Okay. So I will draw this for process in temperature entropy diagram. So 1 to 2 is adiabatic, reversible adiabatic. Reversible adiabatic means isentropic process, right? Isentropic process. So entropy remains constant. So reversible adiabatics are isentropic process that you have learned in your thermodynamics class. So 2 to 3 is constant temperature process. So it is horizontal. 3 to 4 is again adiabatic compression, adiabatic expansion. So this is isentropic. 4 to 1 is again isothermal expansion. So this is the diagram for reverse Carnot cycle TS diagram. So from this diagram you can this temperature and this temperature, T2 equal to T3, T1 equal to T4, that you have to. So this is S1, this is S3. So S4 equal to S3, S1 equal to S2, right? So this is the diagram. Using this diagram, you can calculate the COP or the Q. So here Q absorption takes place, here Q rejection, right? So you know COP is nothing but Q2 by Q1 minus, Q2 minus 1, right? So this was the our diagram. So here Q1, actually for refrigeration it was Q1 by Q2 minus Q1, right? So our figure was like this: Q1, Q2, W. Source, actually source is nothing but here it is T1, okay, here this is nothing but QA, Q absorbed. Q2 is nothing but Q rejected, right? Therefore COP of refrigerator can be Q absorbed by Q rejected minus Q absorbed, right? So this is the equation for COP of refrigerator. So students, from the diagram, this is 1, 2, 3, 4, S1 equal to S2, S3 equal to S4, T2 equal to T3, T1 equal to T4, QA, Q rejected, right? So COP equal to QA by QR minus QA. So how can you get the equation for QA? QA is nothing but T delta S. Q is nothing but T delta S. Here T1 into delta S is nothing but S1 minus S2, right? Or not S2, S4. S1 and S2 are same, right? S1 and so this is the difference between these two uh, entropy. So this is the value of QA, the area under the process 141. Okay. So this is the value of area under 2 to 3 will be the value of Q rejected. It means Q rejected is nothing but Q rejected is, what will be the Q rejected? T2 into S2 minus S3, or S2 minus S3 is nothing but S1 minus S4 itself. So QR equal to T2 into S1 minus S4 itself. QA was T1 into S1 minus S4 itself, right? So COP of refrigerator will be QA by QR minus QA, that will be T1 into S1 minus S4 by T2 into S1 minus S4 minus T1 into S1 minus S4. Since this S1 minus S4 is common, you can cancel this that term. So you will get COP of refrigerator is nothing but T1 by T2 minus T1, right? So this is the equation for COP of a refrigerator. COP of the refrigerator. So in terms of the temperature, in case of COP of a refrigerator working on Carnot, reversed Carnot cycle. When a refrigerator is working with having air as the working fluid and working in reverse Carnot cycle, then the COP of the refrigerator will be T1 by T2 minus T1, where T1 is lower temperature or sink temperature or temperature of space to be cooled. The temperature of space to be cooled. So T2 is source or higher temperature or ambient temperature. The temperature of the space to which heat is rejected. So in various equations, T1 and T2 may interchange. So you don't worry about whether source is cycled as T1 or sink is cycled as T1, whether or the vice versa. So you just make sure that COP is nothing but lower temperature by higher temperature minus lower temperature by higher minus lower. So this is how we calculate COP of a refrigerator, right? So students, what are the limitations of reversed Carnot cycle? So students, you have got the expression for COP of refrigerator working in reverse Carnot cycle. It is T1 minus T2 minus T1, or lower temperature by higher temperature minus lower temperature, right? So how to increase the COP? How can we increase or improve the COP? So COP can be improved if we increase the lower temperature or decrease or decrease. So lower temperature should be increased or higher temperature should be decreased. These are the only possible way by manipulating the temperature of the source of sink to improve the COP of the Carnot cycle, right? So increasing the lower temperature and decreasing the higher temperature. Decreasing the higher temperature means temperature of the hot body or the source should be decreased. So higher temperature T2 is the temperature of cooling water or air available for rejection of heat in the atmosphere or ambient temperature. So and the lower temperature is nothing but the temperature of the space or the refrigerator, the space to be cooled. The lower temperature is the temperature of the refrigerator or space that should be that is required to be cool. Higher temperature is the temperature of the ambient or atmosphere or the cooling water or cooling air available for the rejection of heat by the working fluid, right? So if the temperature of cooling water or air available for heat rejection is low, that is the COP will be high. But in winter, the outside air will be having lesser temperature compared to summer. Therefore, COP in winter T2 will be lower compared to in summer. In summer, T2 will be higher, right? T2 means higher temperature or the outside temperature. So outside temperature, higher temperature must be reduced so that COP increases when T2 decreases. Therefore, in winter, COP will be higher compared to summer, right? In the winter, COP will be higher compared to summer. But actually, we require a refrigerator or air condition mainly in summer, right? But what is the use of improvement in COP in winter? No use. No use. That is the limitation. That is the limitation of Carnot cycle, right? So in winter we may not be using a refrigerator or air conditioner that much often. It is more useful in summer only. But COP of reverse Carnot cycle will be higher in winter compared to summer. So Carnot refrigerator works more efficiently in winter than in summer. So that is the main problem or the limitation of Carnot cycle. Also, if the lower temperature, also T1, the lower temperature increase means COP increase. That is, the lower temperature is high means COP of the Carnot refrigerator will be high. So the lower the temperature, the lower the refrigeration temperature required and the higher temperature of heat rejection to the surrounding, the larger is the power consumption of the refrigerating machine. So students, increasing the temperature of the space to be cooled is not acceptable, right? We are aiming. Our objective is to what? Maintain the temperature of the cooled space. Temperature of cooling space should be lower. We are aiming at maintaining the cooling space at a lower temperature, but according to the equation for COP of Carnot refrigerator, if T1 increases, COP increases. So this is exactly opposite to our objective. So this is another limitation of reverse Carnot cycle. So these are the limitations of reverse Carnot cycle. So you read it once more, or you try to understand. If you have not understood the concept I have explained, you try to read some textbooks, or if you have any doubts, you can directly contact me. Okay. So I hope I understood the working of an air refrigeration system. The cycle, the process, the COP, and the limitations. Okay. So for the time being, I will stop this session. In the next session, we will study another air refrigeration system working on reversed Joule cycle. Actually, you have learned the Joule cycle. Joule cycle. Joule cycle you have learned in power plant engineering or thermal subject. So that is a cycle used in power plant. In case of actually refrigerator is power plant is a work producing plant or work producing cycle. Refrigerator is a work consuming cycle. So in case of refrigerator you have to use reversed Joule cycle. So in power plant you have to use Joule cycle. In refrigerator you have to use reversed Joule cycle. So reversed Joule cycle is called Bell-Coleman cycle. So students, Bell-Coleman. So students, you just refresh your understanding about the Joule cycle. What are the various processes? 4 different processes involved in Joule cycle, and then be ready for the next session. Thank you.